Okay, is it visible now? Is it visible?
Yes, sir. Yes, sir.
Okay.
Visible.
So pseudo capacitor is a second charge storage mechanism in which charge is stored through surface redox reactions. So for example, manganese oxide and ruthenium oxides. These are two very important electrode materials for pseudo capacitive behavior of supercapacitor. Okay, so third one is battery-like electrodes. Battery-like electrodes are based on sluggish redox reactions. For example, nickel hydroxide, cobalt hydroxide, these are battery-like electrode materials. And in this case, we can see a clear and distinct oxidation and reduction peaks, and the current flowing through the electrochemical cell is proportional to the root of scan rate. Okay, so that is the important difference in between pseudocapacitive and EDLC type electrode materials. Okay, so we can combine these electrode materials and fabricate supercapacitors. So if you combine EDLC type electrode material and pseudocapacitive electrode material, so we can call that supercapacitor as asymmetric supercapacitor. So if you have one capacitive electrode and another one is capacitive, again EDLC, so we can fabricate, we can call it as a asymmetric supercapacitor. And if you combine merits of battery materials and capacitive materials, so we call that supercapacitor as hybrid supercapacitor. So EDLC to supercapacitor. So it is very important to know about the difference between capacitor, conventional capacitor and supercapacitor. So here, if you see the schematics, so this is EDLC based supercapacitor. So that means it is mainly made of activated carbon. Both electrodes are made of activated carbon, which is porous in nature. So here you can see that one electrode is negatively charged, another one is positively charged. And these electrolytic ions are moving towards respective electrodes, right? So normally when we say that supercapacitor, so we don't say that it is super battery, right? But we call it as supercapacitor. So of course it is close to capacitor, but what is the difference between these capacitors and supercapacitor? So if you try to understand normal electrostatic capacitor, so electrostatic capacitor is it's well known, and in our 12th we already studied electrostatic capacitors, and even in undergraduation level we have studied about dielectrics and mainly electrostatic capacitors. We have already learned about it. So I would like to give the difference between normal conventional capacitors and supercapacitor. So electrostatic capacitor is made of, so basic simple example of electrostatic capacitor is parallel plate capacitor. So in parallel plate capacitor, we have two metallic plates and a dielectric medium in between. And charge is stored in this particular electrostatic capacitor. Charge is stored in the form of electric field. And capacitance is calculated using formula C is equal to epsilon R epsilon 0 into A divided by D. A is surface area of the electrode. D is difference between the separation of these parallel plates. Okay. And epsilon R and epsilon 0 are the relative permittivity or dielectric constant of medium, or and permittivity of free space, right? So it's from this formula here, if you look at this formula, capacitance is proportional to area and it is inversely proportional to the separation between charges, right? So in a supercapacitor, this A is made very high. So this area of electrode material is made very high, as and that area is in the range of 1500 to 2400 meter square per gram. That's why the capacitance of normal supercapacitor is very high, huge as compared to the capacitance in electrostatic capacitor. So you might have observed in electrostatic capacitor, capacitance is written in the microfarad range. It is very small as compared to the capacitance on supercapacitor. Okay, it is normally in farad, like 100 farad, 200 farad, 500 farad, and so on. So that is the major difference here. So this A part is made very high. The area of the electrode is made very high, and D is nothing but separation of positive and negative charges. So energy storage in supercapacitor is based on EDLC, which is nothing but electric double layer formation. Okay, so I will show you here. This is the diagram in EDLC. So let's say this is electrode material. So why do we call it is electric double layer means because you have negative charges in the electrode surface and positive ions which will be adsorbed on the surface of this negative electrode, right? So that's why we call it as double layer formation. So in this double layer formation, if you look at the separation between these charges, so it is in angstroms. So this D part is made is very, very small. So this D part is made very, very small, and which is in the range of angstrom. So that's why the capacitance of supercapacitor exceeds what the values we get normally for electrostatic capacitors. So if you, I have taken one example here, like if you take a electrode material with, let's say, activated carbon with surface area 1000 meters square per gram, and if you consider average charge density of 30 microcoulomb per centimeter square, and the operating potential is normally in aqueous electrolyte is 1 volt. So specific double layer capacitance can be calculated as 300 farad per gram, and this value is very, very high as compared to the capacitance in conventional uh, electrostatic capacitors. Okay, so another mechanism is pseudocapacitive. In pseudocapacitive itself, we have three important mechanisms, which pseudocapacitive mechanism can be classified into three important mechanisms. So first one is surface redox reaction. So ruthenium oxide and manganese oxide is basically they are surface redox pseudocapacitive materials. And what is difference between these materials and another one is intercalation that I will talk shortly. So in surface redox type materials, the cyclic voltammogram is exactly like it is close to rectangular in shape, and there is no phase change actually when the charge is stored in the material. There is no phase change. So ruthenium oxide or manganese oxide, there is no phase change in the material. That is major difference. And there are continuous change of oxidation states of these transition metals like ruthenium and manganese. Okay, so another type of pseudocapacitive electrode material is intercalation type. So intercalation, one can take any metal, layered metal oxide like niobium oxide is good example of this type of electrode material. Okay, so lithium is intercalated here, and in this case also there is no phase change. So this niobium oxide doesn't, there is no change in the phase of niobium oxide. Second thing is intercalation happens. Intercalation is nothing but this lithium ion intercalates into the insertion host material. So this is also known as insertion of lithium ions into the into this material. Okay, and there is again continuous change of oxidation state. This niobium is also transition metal actually. So there are continuous changes of oxidation and reduction states. So this is the third mechanism, which is known as battery type. In battery type, so simply lithium ion battery can be taken as an example. So one can have graphite as a anode material and any lithium metal oxide as a cathode. So the basic difference between Faradic battery type electrodes and pseudocapacitive electrode is peaks in the cyclic voltammograms are very distinct, like oxidation and reduction peaks are clearly observed here. And the shape of cyclic voltammogram is entirely different as compared to the shape of normal pseudocapacitive electrode materials. So here, one important thing happens is the phase of material changes. If you take the example of nickel oxide or cobalt oxide, they are battery type electrode materials, and when the oxidation and reduction takes place during charging discharging process, this cobalt oxide or hydroxide, their phase changes. So they are converted into cobalt oxyhydroxide, or again it is reversible redox reaction. Okay, so there are some examples of battery type electrode materials like nickel hydroxide, lithium, this lithium oxide, and this LFP, which is very common battery material. Uh, okay, So I would like to tell you about calculation of theoretical capacity. So one can easily calculate theoretical capacity of different materials, and this is one of the important steps of doing our research. So first step is you should know a formula for finding out the capacitance or capacity of your material on which you are working. Okay, so this is the formula, Z into F divided by M. Z is number of electrons in transferred during the electrochemical reaction. F is Faraday's constant, and M is nothing but molar mass. So I have taken one example here, like if you take cobalt oxide as an electrode material, and lithium can be stored into cobalt oxide. So one can calculate a specific capacity of cobalt oxide when lithium intercalates into the layers of cobalt oxide. Okay, so here if you see this reaction, 8 electrons are involved, 8 electrons are transferred. So one can simply substitute value of Faraday's constant and molar mass of cobalt oxide, and one can find out the value of theoretical capacity, which turns around 890.4 milliampere hour per gram. Okay, so similarly, one can find out the theoretical specific capacitance. So cobalt oxide is similarly used for cobalt oxide is also reported as a supercapacitive, super pseudo capacitive electrode material under alkaline conditions. So theoretical specific capacitance can be calculated using this formula, Z into F divided by M into V. So Z is number of electrons involved in the reaction. F is Faraday's constant. M is molar mass, which is 240.80 gram per mole for cobalt oxide, and voltage is normally 0.45 for cobalt oxide. So one can calculate easily the specific capacity and specific capacitance. Okay, so cyclical thermogram wise, there are some differences. Like if you see EDLC and pseudo capacitive, their cyclical thermograms are rectangular in shape, but in case of battery type electrode, you can observe two oxidation and reduction peaks distinctly. Okay, so there are different formulae. So if you have your cyclical thermogram in rectangular in shape or close to rectangular in shape, so you can consider that material as a pseudo capacitive electrode material. Okay, and one can and you should go for calculating specific capacitance using this formula. Specific capacity you should calculate for the materials which show this type of behavior, battery type behavior. So you get clear oxidation and reduction peak. So in this case, you should not report specific capacitance. Instead, you report specific capacity, and the formula for specific capacity is given here. Okay, so similarly in galvanostatic charge discharge, one can calculate value of specific capacitance and specific uh, capacity. So these are the differences. So this plot is for EDLC type electrode material. So let me give. Oh, sorry. Okay, so yeah. So AC impedance spectroscopy is also used to find out different parameters like ESR, equivalent series resistance of the electrode material, and the charge transfer resistance of the electrode material. So it is simple electrochemical technique, and one can extract these important parameters for supercapacitors. Okay, so this is the information on how the Nyquist plot of this particular double layer capacitive and pseudo capacitive and battery type electrode materials are different. So if you see here the double layer behavior, so in this double layer capacitor, the Nyquist plots are like this, and in pseudo capacitives, you could see the semicircle in the high frequency region, and the straight line again in the lower frequency region. So it is capacitive behavior of the electrode. Okay, so no problems. I will go to present my work. So we have fabricated alpha cobalt hydroxide, and we doped cerium into it. So we chose to work on cobalt hydroxide because of these advantages. First of all, it has very high theoretical capacity, and the value is up to 2076 coulomb per gram. it is layered structure and it has large interlayer distance. So it is shown in this schematic. So cobalt hydroxide has only disadvantage as their lower cyclic stability and poor conductivity. So in order to improve its poor conductivity and cyclic stability, we chose to dope alpha cobalt hydroxide by using cerium. And why did we take cerium? Means actually cerium, any dopant, if you introduce into a material, their chemical, physical, and catalytic property changes. Basically, the electronic structure of this material changes, and therefore we decided to use cerium as a dopant. And one more reason for choosing cerium is because it has two oxidation states, cerium 3 plus and cerium 4 plus, which again, which are helpful in electrochemical energy storage. So and also from the literature, it has been seen that there are 5-fold increment in the capacitance of nickel oxide, which was reported recently. And the electronic structure changes, as I said previously. Okay, so we used this, we prepared alpha cobalt hydroxide using electrodeposition method, and we doped cerium into it. The deposition parameters are shown here, and we prepared different samples actually, right from 0% cerium to 3% cerium, and the deposition mass was is also given in this particular table. So from X-ray diffraction, we found the structural properties of cerium doped alpha cobalt hydroxide. So there is no significant change in the crystal structure of alpha cobalt hydroxide. So in order to confirm the formation of in the presence of cerium in the cerium doped alpha cobalt hydroxide, we chose to go for XPS analysis. And from XPS, it is seen that cobalt and cerium and oxygen, these elements were present in the sample. So in order to find out the oxidation states of cobalt hydroxide, so we went for high resolution TEM spectrum, and from this image we can confirm the CO2 plus, the cobalt is present in two oxidation states, CO2 plus and CO3 plus states. Actually, cerium was very small. The amount of cerium was very small. It was just 1% cerium. So it was not found in XPS. So we went for XRF analysis, and from XRF we found that cerium is 1% in, sorry, excuse me. Okay, so and furthermore, in order to understand the morphological analysis, we subjected our sample for FESCM and TM analysis, and we found that when the cobalt hydroxide is doped with cerium, the morphology changes significantly. So for 1% cerium, so initially, if you look at this image, so initially nanoflakes were grown in different way, but when alpha cobalt hydroxide is doped with cerium, they were grown in horizontal way, and the structure becomes more microporous in nature. And further addition of cerium into cobalt hydroxide, so the agglomeration takes place, and the very compact microstructure is formed. And again, in order to see the micro structure of this cobalt hydroxide, the cerium doped cobalt hydroxide, so we went for TM analysis, and from TM, high resolution TM analysis, we confirm that these nanoflakes are formed with porous nanosheets, which is clearly visible from this image. So we also estimated electrochemical active surface area of the electrode material, and we found that, so our undoped sample showed maximum active surface area of 0.59 meters square per gram. And when we dope alpha cobalt hydroxide using cerium, the surface area increased to 0.66 meters square per gram. Okay, so supercapacitor performance was carried out using cyclic voltammetry and galvanostatic charge discharge. And we found that the specific capacity of 1% doped cerium doped cobalt hydroxide increased by 66.7%, and maximum specific capacity is obtained as 450 coulomb per gram. And we got very small IR drops. It also indicates good conducting behavior of the sample. So this is electrochemical reaction corresponding to charging and discharging process of cerium doped alpha cobalt hydroxide. So EIS is also done again in order to extract electrical parameters such as ESR and RCT. ESR is nothing but equivalent series resistance, and RCT is charge transfer resistance. So this is equivalent circuit which was fitted for this impedance data. And from this we can see that when cobalt hydroxide was doped with 1% cerium, the charge transfer resistance reduced, and this is mainly because of the good conducting behavior of 1% cerium doped alpha cobalt hydroxide. And furthermore, we studied the cyclic stability at 20 ampere per gram, and we got maximum stability up to 73% for 1% cerium doped cobalt hydroxide. So this is a good achievement, we think. Okay, so we used a specs characterization in order to find out the capacitive and diffusion controlled contribution of uh, 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 contribution of this electrode. So here we found that for in case of undoped cobalt hydroxide, the capacitive contribution was 38%, and when cobalt hydroxide was doped with 1% cerium, the capacitive contribution increased to 45%. So furthermore, we fabricated hybrid devices using activated carbon as a negative electrode and 1% cerium doped cobalt hydroxide as a positive electrode. So this is the performance of a hybrid device. So we got maximum energy density of 14 watt hour per kg at power density of 400 watt hour per kg, and this value is quite high as compared to the literature, as compared to the reported supercapacitor devices. So in our second work, we actually we tried to we were trying to improve the value of the performance of alpha cobalt hydroxide. So in our first attempt, we used cerium doping. In second attempt, we used surface modification of alpha cobalt hydroxide using Maxine. So Maxine is very interesting electrode materials, and they are its general formula is n plus 1 a xn. So where m is transition metals which are taken from this part of periodic table. A is generally aluminum, silicon, phosphorus, and so on. And X is X can be carbon or nitrogen. So there are three types of maxins, maxins which are shown here. So there are different advantages of maxins. First of all, they have very large interlayer spacing, which is quite helpful for electrochemical reactions. It has excellent electronic conductivity. Again, it is very helpful for electronic diffusion in the electrode. So that's why it is and that's why it is used for supercapacitor application. So fourth important point is hydrophilic nature. So since it is hydrophilic in nature, so it can be used in aqueous electrolytes, and which provides intimate contact in between electrode and electrolyte. So its thickness is also controllable. One can simply deposit this slurry on electrode material, and it has large surface area because it is made of two-dimensional materials, and it provides very huge surface area or electrochemically active sites for electrochemical reaction. So in this work, we used again electroporation method for preparation of alpha cobalt hydroxide, and Maxine was synthesized using this procedure. So this procedure is given here. Okay, so this is actually surface modification of alpha cobalt hydroxide. So initially we used max phase. Again, we etched out the aluminum layer in the max phase, and we get layered Maxine material over here. Okay, so once we get Maxines, we get Maxine in the form of ink, and we used this ink to surface modify the alpha cobalt hydroxide. So alpha cobalt hydroxide was prepared using electroporation method, and this modification is made over here. So different concentrations of Maxines were used. So first, this is actually unmodified alpha cobalt hydroxide. This image is alpha cobalt hydroxide is modified with 0.05 milligram per centimeter square, and here this alpha cobalt hydroxide is modified with 0.3 milligram per centimeter square. So this is how we modify the surface of alpha cobalt hydroxide, and we went for X-ray diffraction again to confirm the formation of alpha cobalt hydroxide, MaxIn and max phases, and we successfully showed that the materials were formed. And from XPS also again we confirm the formation of this cobalt hydroxide and MaxIn and MaxIn material. Okay, so this is morphological analysis of MaxIn. So first, this first image shows the FACM image of max phase, which is normally bulky and close packed structure. When aluminum layer is etched out from the material, it becomes accordion-like structure, two-dimensional structure. And this is high resolution TM image of MaxIn nanosheets. So this is very high magnification of TM magnification of MaxIn, which clearly shows that this MaxIn is formed of layered structure, and these are layered materials. So again, the high resolution magnification of this part is shown here. So it shows the fringes, the thickness of the fringes is around 0.25 nanometers, and which corresponds to 100 plane. So this is SAD pattern. From this it seems that it also supports the formation of MaxIn here. And these final images which are shown in the bottom, uh, those images indicate the uniform distribution of titanium, carbon and oxygen. So this is surface modified alpha cobalt hydroxide. So one can see here, this surface is actually unmodified alpha cobalt hydroxide. So there is nothing on the surface of alpha cobalt hydroxide. But once the surface is modified with 0.05 milligram per centimeter square, surface slightly gets modified. And again, the further addition of MaxIn changes the surface significantly. And if we put too much of MaxIn on the surface of alpha cobalt hydroxide, the separate layer of MaxIn is formed on the surface of alpha cobalt hydroxide. Okay, so in order to understand its capacitive behavior, we studied its cyclical voltammetry and galvanostatic charge discharge curves. And from cyclical voltammetry, we estimated values of specific capacity, and we got maximum value of specific capacity for alpha cobalt hydroxide, which was modified with 0.05 milligrams. Excuse me. Okay, so again, galvanostatic charge discharge was performed to estimate the values of rate capability and specific capacities. So here you can see that when surface of alpha cobalt hydroxide was modified with 0.05% milligram per centimeter square of MaxIn material, the capacity retention of sample increased a lot. Because here for alpha cobalt hydroxide, pristine alpha cobalt hydroxide, the rate capability was only 52%. But when the surface got modified, the rate capability increased up to 76%. And the higher rate capability is always preferred for fabricating power performance, high power supercapacitors. So from EIS, equivalence, electrochemical impedance spectroscopy, so we got different parameters like the ESR equivalent series resistance and charge transfer resistance. So for sample which were modified with 0.05 milligram per centimeter showed the smallest value of charge transfer resistance, and the smallest value is attributed to the high conducting behavior of MaxIn and optimum concentration of MaxIn on the top of this alpha cobalt hydroxide. So deconvolution of capacitive contribution is done. So by using this formula, I is equal to AVP V power B. So A and B are adjustable constant and V is scan rate. So from this one can find out value of B, and from B, the value of B, we can guess which kind of material is this, whether it is pseudo capacitive or whether it is battery type electrode material. So we got B value as 0.66 for oxidation peak, and for reduction peak the B values was 0.58, and this is close to battery kind of behavior. Okay, so when sorry, so when we modify this alpha cobalt hydroxide with this 0.05 milligram per centimeter square, the B value significantly changed. Like if you look at this image, so B value changed. For oxidation peak it changed to 0.73, and for reduction it changed to 0.69. So actually this modification, due to this modification, the electrode become more more capacitive character. Okay, so that is one achievement I would like to tell here. So Dunn's method is used to deconvolution of to find out the capacitive and diffusion controlled contribution of electrode material. So here the capacitive contribution is increased by 4%. Now you can observe here for unmodified electrode, the capacitive contribution was 52% only. But when the electrode is modified with 0.05 milligram per centimeter square, so we got 56% of contribution from capacitive. And this is very important study through which one can prepare materials with more capacitive character, and we can combine them to fabricate hybrid supercapacitor. So this is characterization, electrochemical characterization of Maxine. So Maxine is very highly conducting electrode material. That's why we get very small ESR here, 1.2 ohm. And excuse me. Okay, so I think due to very limited time, so we have to go little rapidly. Okay, so we fabricated devices here uh, by using Maxine and activated carbon, and we got really high energy density for the device, which device fabricated through Maxine as a negative electrode. So we got for maximum energy density of 44.5 watt hour per kg. Okay, so again from the Regon plot, we can put these values in the Regon plot, and we can compare our values with the literature, and we found really superior values of energy densities and power densities. Stability wise, this supercapacitor shows 72% of stability after 5,000 cycles, and it is also acceptable. So we demonstrated some devices here. So we fabricated Swaglok cell type supercapacitors, which are shown here in this image. So we again went for flexible supercapacitor fabrication, and we got maximum energy density of 1.17 milliwatt hour per centimeter square. So in our second work, we prepared cobalt, nickel, iron layer double hydroxides. Similarly, we uh, uh, executed uh, structural, morphological, and electrochemical analysis of those samples, and from this we can conclude that ternary layer double hydroxides have greater advantages as compared to binary layer double hydroxides, which can be clearly seen here. The maximum specific capacity is obtained for ternary layer double hydroxide was 360 coulomb per gram, and which is quite higher as compared to other binary layer double hydroxides. In this study, we used we tailored the composition of ternary layer double hydroxide, and yeah. So I would like to show the capacitive performance of this. So here we have got maximum. Sorry, yeah. So here again I would like to show this images. Yeah. So for for ternary layer double hydroxide, we changed a different concentrations of these metal ions. So we made three types of electrode materials. One is cobalt rich, another one is nickel rich, and third one is iron rich, cobalt nickel iron layer double hydroxide. So we got the maximum good performance for nickel rich CNFL sample, and we found maximum specific capacity of 467 coulomb per gram. Okay, so we are again tested this electrode for electrocatalytic application, and those are presented here. So we got the maximum minimum over potential up to 136 millivolt, and which is for nickel rich CNFL sample. And Tafel plot also showed uh, like 46 millivolt per decade. And this is also a good achievement for this type of material. Okay, so in conclusion, we actually implemented four different strategies to improve performance of alpha cobalt hydroxide. So we used a cerium doping to improve its performance. Second one, we modified alpha cobalt hydroxide surface by using Maxine. And in third work, we prepared layer double hydroxides uh, by introducing third trivalent metal cations into cobalt hydroxide. And finally, we successfully optimized the composition of ternary layer double hydroxide. So I would like to acknowledge DST Inspire program, Department of Science and Technology, BRC. I'm also thankful to Shastra University for providing all the support. I'm also thankful to these people who are listed here. So they have helped us a lot during our research journey. Okay, so I'm also thankful to these are members of our group. So Dr. R.C. Rohit is already graduated from our lab, and he's currently working in IIT Hyderabad. So there are some current PhD students, they are working under my guidance in our laboratory, and some MSc students also already worked in our lab, and some people are already working for their post-graduation research. Okay, thank you so much for your patience, and yeah, if you have any question, you can please ask. Any question? Yeah, actually there is one question from yeah, one of the audience. Can we synthesize Maxine at low temperature? So actually Maxine uh, cannot can be prepared, because Maxine and max phases are different actually. So max phases cannot be prepared at low temperature. So far the maximum temperature used for max phases is reported up to 700 or 800, that too in molten solvents. But for Maxine, we can simply prepare it at room temperature. So there is not a big deal to prepare Maxine, but we have to prepare it from max phases. Yeah, this is first. Yeah, only one question was there. If you have any other question, you please. Yeah, the second question is from Patil Sumita. Yeah, is it correct to HKL planes as 003, 006, or 111? No, actually it is 003 only, 003, 006 for LDHs. These are the characteristic peaks for LDHs. So I'm not sure about 111 and 222. Where did you see it? So 003 and 006 are correct planes. No, she's saying that from calculation 111 is coming. I don't know what calculation you're referring, but yeah, If you look at the GCPDS card number, if you if you go through the GCPDS card, it is 003 peak and 006. These two peaks are characteristics for layer double hydroxides.
Thank you, sir. Sir, the way in which you are explaining topic is really amazing. We teacher, student and researchers are highly benefited by your speech. On behalf of Balwan College Vita, we would like to express deep sense of gratitude for online joining to us. Thank you much. Thank you very much, sir, once again. And I declare that this session is over here. Thank you. Thank you very much, sir.
Okay, thank you so much for inviting me. And again, thankful to all the organizing committee for inviting me. And thank you for your patience also. You are waiting for a long time. Okay, thank you so much. Thank you, everyone.
Thank you very much, sir.
Thank you.
Thank you, madam.
Principal Dr. R.S. Manik, Balawan College, Beta. Head Department of Physics, Dr. C.R. Bobre, as well as organizing committee members of this conference to give me an opportunity to speak in front of you. Topic of my presentation is synthesis of nanomaterials for gas sensing applications. Here, okay. Now, outline of my presentation is introduction about nanomaterial, types of nanomaterial, classification of nanomaterial, applications of nanomaterial, synthesis method of nanomaterials, and synthesis of nanomaterials by oxalate co-precipitation method. Here we have to discuss about the synthesis of nickel zinc ferrite nanoparticles, lanthanum substituted NiCuZn nanoferites, and finally MgZn added silver nanoparticles in the form of nanocomposites. And here we have to learn about also characteristics of nanomaterials as well as DC electrical resistivity and gas sensing behavior of nanomaterials. Now, introduction. Nanomaterial means the dimension of material is about 1 to 100 nanometer. 1 nanometer means 10⁻⁹ meter. Now, this material plays an important role in the fabrication of many devices, application in the various devices as well as industries because of their unique chemical and physical properties such as large surface area to volume ratio and their high mechanical strength. Now here we have to display the comparative of nanoparticles with other known nanoparticles. 1 angstrom in it is the dimension of atom. Now molecule having size about 1 nanometer, DNA having size about 10 nanometer, viruses size is about 100 nanometer, bacteria having size 1 micrometer. Now blood cells having diameter about 10 micrometer, human hair is about diameter 100 micrometer and having diameter is about 1 mm, and finally ball is about diameter 1 centimeter. This is a comparative chart or comparative of nanoparticles with other known particles. Okay. Now types of nanoparticles. On kind of materials, there are 4 types of nanoparticles: inorganic nanoparticles, organic nanoparticles, carbon nanoparticles, and composite based nanoparticles. Inorganic based nanoparticles includes metals and metal oxide nanoparticles. Now silver, gold, aluminum, cadmium, copper, iron, and zinc is an example of metal nanoparticles or inorganic based nanoparticles. There are also available metal oxides: zinc oxide, copper oxide, magnesium, aluminum oxide, titanium oxide, etc. is an example of inorganic based nanoparticles. Similarly, carbon based nanoparticles include single walled carbon nanotubes, multi-walled carbon nanotubes, carbon fibers, and activated carbon as well as carbon black is examples of carbon based nanoparticles. Organic includes liposome, ferritin, and micelles, while composite based nanoparticles consist of combination of metal oxide based as well as carbon based and or arsenic based nanoparticles. Now, classification of nanoparticles. Dimension based classification of nanoparticles is divided into 4 parts: 0 dimension, 1 dimension, 2 dimension, 3 dimension. Now, atomic clusters, rings, quantum dots is an example of 0 dimension nanomaterials. Spiral springs, fibers, filaments, and nanotubes is an example of 1 dimensional nanomaterials. Nanodiscs, nanolayers is an example of two-dimensional nanomaterials. Embedded clusters, equiaxial crystallites is an example of three-dimensional nanoparticles. Now here, the common features of nanoparticles. Nanoparticles can be amorphous or crystalline. Nanocrystalline can be single crystalline or polycrystalline, exhibit various shapes and forms. Here we have to display the shapes, morphological shapes according to dimensional of nanomaterials. That is, cluster is included among 0 dimension, nanotubes having 1 dimension, films and coats having 2 dimensions, polycrystals having 3 dimensions, and it can exhibit or exist individually or incorporated in a matrix also. It can be metallic or semiconducting or insulating behavior. Now some morphological nanoparticles. Now this is a nanoporous palladium nanoparticle having 0 dimension. This is the second. This is the graphene nanoseeds having 2 dimension nanoparticle. This is the Ag, that is silver nanorods having 1 dimensional nanoparticle. This is the polyethylene oxide nanofibers having 1 dimensional nanoparticle. This is the nanowires of zinc oxide having 3 dimensional nanoparticles. And finally, nanowire network having 3 dimensional nanoparticles. Now this is the photo gallery of some nanoparticles. Nanosphere of gold, here nanosphere of polymeric hydrogel, nanosphere of silica, nanorods of carbon, nanocapsules, here self-assembled nanoparticles having nacelles. It can be used as a polluting monitoring sensors and a few applications. Okay. Now this is the application of nanoparticles with morphological. Now graphene is used in the semiconductor, batteries, electronics, composites and industries, while correlance is used in the biomolecular addictions, and nanotubes used in the transistors, solar panels, nanowires used in the potentially nanowires used in the high density storage device, as well as digital electronics, nanocones used in the chemical sensor, biosensors, spectroscopy, batteries. Now quantum dots used in the transistors, solar cells, diodes, lasers, LEDs, photocatalysts, and nano clusters are used in the biotechnology and pharmacology. Now synthesis of nanomaterials. There are 2 basic methods of synthesis of nanomaterials. First is the top-down approach method and second is the bottom-up approach method. In top-down approach method, building down or crush down the particles in the form of nanoparticles, while in bottom-up approach, build up the nanoparticles in the form of clusters as well as nanoparticles. Now, physical method, chemical method, as well as biological methods in the followed by top-down and bottom approach methods are discussed or labeled here. Lithography technique, arc discharge method, mechanical grinding, milling, spray pyrolysis techniques are used to fabricate nanoparticles, followed by the top-down approach method, while co-precipitation method, sol gel method, electrochemical method, hydrothermal method, sonochemical method are used to fabricate nanomaterials under top-down approach method as well as bottom-down approach method. While using plant and their extracts as well as using micrograins, using LX or using enzymes, we can prepare nanomaterials under bottom approach method. Now we can also fabricate nanomaterials by using thin deposition techniques. These are chemical methods, and this is the chemical methods, and this is the physical methods. We can prepare also nanomaterials by using thin film deposition techniques. Now here we have to now key issues or challenges in the fabrication of nanostructured materials. Can you control the particle size? Can you control the shape of nanoparticles? Can you control the structure, either crystalline or amorphous? Particle size distribution. Now synthesis of nanoparticles under presentation. Here in our lab, we have to prepare, or our students prepare nanoparticles in the form of nanofarads. That is rarer the substituted zinc ferrite, samarium, lanthanum, and yttrium substituted nickel zinc ferrite nanofarads can be prepared by using oxalate co-precipitation method. As well as we have to prepare lanthanum substituted NiSiZn ferrites and Az doped MgZn ferrites in the form of nanocomposite or nanofarads. Now, method of co-precipitation method can be discussed by using this method. Next, okay. Now, this is the synthesis procedure of oxalate co-precipitation method. Okay, by taking nickel sulfate, zinc sulfate, cadmium sulfate, or we can dissolve these sulfates in double distilled water and complete the dissolution by adding concentration H2SO4 and maintain the pH of the solution is about 4.5. And after dilution of these sulfates, place the solution on the hot plate and heat the solution for 80 degrees Celsius for 2 hours. And then after cooling, added ammonium oxalate solution, that is saturated ammonium oxalate solution, in order to get the precipitate. Till we have to get final precipitate by or of oxalates of nickel, copper, zinc, iron, lanthanum. And this oxalate precipitate solution is then placed on a hot plate or placed on a sink bath and then filtered by using Whatman paper number 41 and suction pump. And this filter or precipitate is washed several times in order to remove the sulfate ions. And removal of sulfate ion can be confirmed by barium chloride test. And finally, this precipitate is dry under neon lamp. And finally, we have to pre-sintered and sintered this sample in a furnace. Okay. And we have to use some tools, that is TGDT, XRD, FTR, FESM, and SM tools are used to characterize the nanofarads. And these are some parameters, that is lattice constant, X-ray density, porosity, crystallite size, bond length, ionic radii can be calculated by using these formulas. While this is the now here we have to measure also DC electrical resistivity, that is two-probe method is used to measure DC electrical resistivity of our samples, as well as we have to measure gas sensing measurement by using two-probe method. Okay, now this is the TGDT analysis. From this this is the typical TGDT of our one sample. This shows that initially there are two steps in a TGA curve. In first step, there is a weight loss about 20.69 and is observed in the range from 137 to 221 degree Celsius, corresponding to endothermic peak. Endothermic peak. This is the endothermic peak. And in second step, we have to get weight loss is about 34.88, corresponding to exothermic peak. Existence of endothermic and exothermic peak in TJ-DT analysis confirms the formation of phase of our material. And here we have to decide the temperature of our material is about 346 degrees Celsius. Now this is the X-ray diffraction patterns. Now this is the X-ray diffraction pattern of lanthanum substituted nickel zinc ferrite. This is the X-ray diffraction pattern of samarium substituted nickel zinc ferrite, and this is the X-ray diffraction pattern of yttrium substituted nickel zinc ferrite. It is observed from this X-ray diffraction pattern is that the existence of the plane lights 220, 311, 400, 422, etc. indicates that the formation of single phase or cubic spinel structure, in addition to secondary phase due to orthoferrite phase. It means that orthoferrite phase is due to lanthanum, samarium as well as yttrium. From this diffraction pattern, it is also indicates that by substituting lanthanum as well as samarium in place of iron, intensity of diffraction pattern decreases. Intensity of diffraction pattern decreases. It means that orthoferrites or rare earth obtain or create strain on lattice, and that is why the intensity of the patterns or intensity of the peaks are decreases. While in case of yttrium substituted nickel zinc ferrite, there is no any variation observed in the intensity of the peaks, because yttrium is completely exists in the lattice. While in case of both these patterns, lanthanum as well as samarium does not enter in the lattice, and that is why the lattice constant of lanthanum substituted as well as samarium substituted nickel zinc ferrites are decreases with increasing rare earth content, and this may be due to the formation of isolating layer or isolating thin layer around the grain boundaries rather than entering in the lattice, and therefore the lattice constant of samarium as well as lanthanum substituted, this is the samarium. So the red indicates the samarium, and this line, black line, indicates the lanthanum, and last is the blue line is the variation of lattice constant with the yttrium constant. But in case of yttrium, the lattice constant increases with increase in lattice constant of NiZn ferrite increases with increase in yttrium content, because here we have to replace smaller size of iron with larger size of ionic radii, that is rarer, and that is why the lattice constant of nickel zinc ferrite increases with increasing yttrium content. Now this table shows structural data of rare earth substituted nickel zinc ferrites. This data shows that the physical density of our sample measured by using Archimedes principle is 98% to that of a X-ray density. Crystalline size of the sample is lies in the nano size range. It means that our ferrite prepared in the form of nano size, and this indicates that the crystalline size decreases with increasing lanthanum content as well as samarium content. But in case of yttrium substituted nickel zinc ferrites, crystalline size increases with increasing yttrium content. The decreasing trend of crystalline size for lanthanum substituted as well as samarium substituted nickel zinc ferrite may shows that there is a strain occurs on the lattice of the ferrites. Here also we have to calculate or obtain the values of bond length and ionic radii on A side as well as B side. The train of bond length as well as ionic radii on A side and B side shows same as that of a lattice constant. Now here we have to also calculate X-ray density. Now here X-ray density of lanthanum substituted nickel zinc ferrite increases with increasing lanthanum content. It means that mass overtakes the increasing volume. Mass overtakes the increasing volume. And this trend is followed also for the samarium substituted nickel zinc ferrite. But in case of yttrium substituted ferrite, the X-ray density decreases with increasing yttrium content. Now physical density, okay, this is already explained. Now this is the XRD analysis of lanthanum substituted NiCd ferrites. Now here existence of these peaks indicates that formation of again cubic spinel structure in addition to orthoferrite phase due to silver. Here we have to get the silver phases or metal silver phases. And these phases are observed at an angle 38.13, 44.27, 38.18, 44.33, as well as 38.19 and 24.36 due to metal silver, and which is exhibit according to JCB card. And these are the some parameters also calculated for this sample. It is observed that lattice constant of silver added MgZn ferrites decreases with increasing Ag content. It means that silver having larger size as compared to iron, but it cannot enter again into the lattice. It forms grain boundaries around the grains, and that is why here we have to get increasing trend of lattice constant. Decreasing trend of lattice constant with increasing Ag content. Here the crystallized sites of MgZn ferrites shows a decreasing trend, initially decreasing trend and then increasing trend. There is no any lateral verification or linear verification of the crystallite size. Here X-ray density of the ferrite increases with increasing Ag content. Bond length and ionic radii also shows same trend as that of a lattice constant. Now this is the FTR or infrared spectroscopy of our sample. This is the IR spectra of lanthanum substituted nickel zinc ferrite. This is the IR spectra of samarium substituted nickel zinc ferrite, and this is the IR spectra of yttrium substituted nickel zinc ferrite. Now here we have to observe two main absorption bands near about 400. This is 400 and 600. For every sample we have to get two absorption bands near about 400 and 600, and which is suggested by the scientist to order on, indicates that the exact formation of ferrite. Also here we have to calculate the value of wave numbers, and these wave numbers are displayed in the table, indicates that due to substitution of lanthanum, samarium and yttrium, tetrahedral site or wave number corresponding to tetrahedral site displaces to lower frequency site, indicates that lanthanum, samarium as well as yttrium occupies B side of the ferrite. This is the FTR spectra of lanthanum substituted NiCd ferrites. Here again we have to get two main absorption bands near about 400 and 600 per centimeter. Also indicates that well formation of ferrite by using oxalate co-precipitation method. Under investigation, it is observed that oxalate co-precipitation method is very well method to prepare ferrite as compared to sol-gel method as well as sol-gel autocombustion method as well as another chemical methods. Therefore, here or in our lab, we have to choose only oxalate co-precipitation method. Here we also display the data about wave numbers mu1 and mu2 corresponding to tetrahedral and octahedral sets. Now this is the okay. This is again FTR spectra of AZ doped MgZn farads. Again, we have to get same things, but here we have to observe that there are some shoulders appear in the octahedral side, and this is due to Jahn-Taylor effect. It means that our sample consists of excessive Fe2+ ions. Okay. Here we have to display the scanning electron microscopy. This is the microphotographs of our samples. These samples indicates that the well formation of grains by using oxalate co-precipitation method with the lanthanum, samarium as well as yttrium substitution, grain size decreases. Grain size of the NiZn farads decreases with the substitution of lanthanum, samarium as well as yttrium. And this is the most advantages of our sample. If we decrease the grain size, then it can be more useful in the gas sensing purpose, as well as in the improving the electrical as well as magnetic properties. If we improve the electrical as well as magnetic properties, then this type of material can be utilized in the electronic component or fabrication of electronic component. And that is why here we have to choose this method and prepare such type of a farads, nanofarads. Now this is the scanning electron microscope of AZ doped MgZn farads. It is a well prepared farad. This again indicates that here we have to get very small grains in the form of sphere, and the grain size of the sample is about 39, 32.2, 29.4. It means that the grain size of MgZn farad is decreases with increase in Az or increase in silver content. Now this is again FSM of lanthanum substituted NiCuZn farads. This again shows same trend. This is the grain size of samples. Again shows decreasing trend with increasing lanthanum content. Okay. Now EDAX analysis. The presence of the planes like nickel, copper, zinc shows that we have to prepare stoichiometric form of nanofarads conferred from this EDAX. Now this is the atomic percentage of metal ions and weight percentage of metal ions. This also confirms the well formation of farad in the stoichiometric form. Now the DC electrical resistivity of our samples. Now this is the okay. Okay, this is the DC resistivity or DC electrical resistivity of AZ doped MgZn farads. There are three main regions for this farad. First region is shows the conduction mechanism is due to impurity. Second region is due to ferrimagnetic region, and third region is a paramagnetic region. Here we have to get the dip at the ferrimagnetic as well as paramagnetic curve, and is called as Curie temperature. It means that here, as temperature increases, resistivity decreases. Indicates that the semiconducting behavior of our sample. Here we have to display the room temperature resistivity of our sample, and this values shows that resistivity, room temperature resistivity of sample decreases with increasing Az content, and therefore this sample are more useful in a gas sensing purpose. This is the Curie temperature data of our sample. If we do Az content in the farad, then the Curie temperature decreases, because Az does not plays or Az plays role of conducting mechanism. But here we have to study the resistivity, and that is why the resistivity, Curie temperature is decreases with increasing AC content.
Time is over, sir. Please.
Okay. Now gas sensing mechanism, main part. बघा. Fine. Okay. Any question?
Appeal for the delegates on the end of this convention or conference. Want to ask a question? Please ask them that.
Any question? There are 15 slides. It is impossible to complete within few minutes. That is why I have to extend all that things in the running pattern.
Thank you, sir. Thank you very much. I'm very proud of Dr. P.J. Shinde sir, who continued his research with common students at college level at KRP Kanya Mahavidyalaya Karegaon, sorry, Islamabad. So he explained with his topic synthesis of nanomaterial for gas sensing. He gives the introduction of nanoparticles, types of the nanoparticle, classification, features, morphology, some photography of the nanomaterials, applications of nanomaterials, synthesis of nanomaterials, thin film development of nanomaterials. Also, he explained the experimental and research components of various elements in their research laboratory, like characterization of nanomaterials, and lastly, concludes how the grain size of the ferrite materials, the ferrite nanomaterials are very useful for electrical and magnetic properties. So I'm very thankful again, Dr. P. Shinde, to give the fruitful information regarding this nanotechnology. Thank you.
Thank you.
Now, I would like to request Professor Dr. U.K. Mohite sir to present bouquet to resource person Professor Dr. E.J. Shinde sir. I would like to request Ms. R.B. Gadge madam to present the bouquet to chairperson Dr. U.K. Mohite sir, Head Department of Physics. MBSK Kannam. I would like to request Miss R.B. Gadge ma'am to present the bouquet to Dr. Pisar ma'am. Okay, now we will continue validatory function. weekly function will begin in 5 minutes. Please wait.
Last, yeah.
पढ़ते सर भैया तो मैडम या
Now it's time for prize distribution of poster presentation, for which I am inviting on the stage Mr. D.B. Patil sir to announce the names of the winner.
Good evening, all of you. The last and the most awaited session of today's conference is waiting of prize distribution. So we first of all thank you all the dignitaries on the dais and off the dais to attend to present at their conference. So without any delay, we discuss the names of candidates who get prize. So consolidated prize goes to the Priyanka Gharge, Balwan College, Beta. May I request to Jimmy Thorat sir, please felicitate her. Next consolidated prize goes to the Patil Prakash Shamrao from KRP College, Islampur. Please come, sir. May I request Ubde sir to felicitate Patil sir. Now third prize goes to the YCIS College, Satara, Mr. Suhas Hari Sutar. Please come, sir. May I request Professor Dr. T.J. Shinde sir to felicitate Suhas. And the second prize goes to the Sagar Ingole. May I request UK Moite sir to felicitate Sagar. And the first prize goes to the once again KRP College, Islampur, Mr. Pawar Amol. Please come, sir. May I request Miss Tisal Madam to felicitate Amol. Sorry. Okay, thank you all the participants who got the prize. Once again, and I raise my proposition. Thank you.
Thank you, D.B. Patil sir. Congratulations all participants. I request if anyone wants to give feedback about the conference, please come on the stage.
1-2 मिनिटांमध्ये कोणाला तरी बोलावं डेलिगेट्स मध्ये रिसर्च स्टुडंट्स मोस्टली
थोडक्यात बोला
First of all, thank you
Colon College Utah for organizing this one-day national conference. And म्हणजे मराठीत बोलतो फर्स्ट प्राइज किंवा सेकंड किंवा थर्ड असं काही नसतं. आपण जे वर्क करतो ते ऑनेस्टली करत राहायचं आणि ते प्रेझेंट करायचं आहे किंवा दाखवायचं आहे असा काही भाग नसतो. काम करतो ते करत राहा, त्याचे बेनिफिट्स तुम्हाला मिळत राहतील आणि या कामातून जे रिसर्चचं म्हणजे संशोधनाचं काम आहे जे समाज उपयोगी काम आहे. सो ती फक्त थीम लक्षात ठेवायची की आपल्याला समाजासाठी काम करायचंय आणि ते रिसर्चच्या माध्यमातून करायचं. प्रत्येक जण त्याच्या फील्ड मधून समाजासाठीच काम करत असतो. आपण रिसर्च हे फील्ड निवडलंय. सो याच्यातून आपण समाजासाठी कसं चांगलं काम करू हे फक्त लक्षात ठेवून काम करत राहायचं. त्याचे बेनिफिट्स आपल्याला मिळत राहतील आणि या पद्धतीचे कॉन्फरन्सेस असेच ऑर्गनाईज करत राहा. आम्ही नक्की पार्टिसिपेट करू आणि इथून पुढच्या वर्ल्ड कॉलेज विटा फिजिक्स डिपार्टमेंट आणि ऑर्गनायझिंग कमिटी यांना खूप शुभेच्छा. अशाच कॉन्फरन्सेस ऑर्गनाईज करून चांगले सायंटिस्ट घडवा, चांगले रिसर्चर्स तयार करा अशी मी थँक्यू.
Thank you. Now I would like to request Mr. D.K. Dhomre sir to propose vote of thanks.
सॉरी मी ऑफ द ट्रॅक जरा थोडासा हे केलं, 2 मिनिटं मागून घेतल्या. आजच्या या व्हॅलिडिटी ट्री फंक्शनचे अध्यक्ष आमचे मित्र प्राध्यापक थोरात सर, प्रमुख पाहुण्या डॉक्टर पिसाळ मॅडम, सर्व व्यासपीठावर असलेले मान्यवर आणि विद्यार्थी. ही कॉन्फरन्स आम्ही फक्त 15 ते 20 दिवसामध्ये याची तयारी केली. आमचा स्टाफ 8 जणांचा आहे, विद्यार्थी आहेत. BSc ला विद्यार्थ्यांची संख्या, MSc ला विद्यार्थ्यांची संख्या याच्याबद्दल जी काही वस्तुस्थिती आहे ती सकाळी राजपुरे सरांनी बोललेली आहे, ही वस्तुस्थिती आहे. तर आम्ही अतिशय कमी वेळात या ठिकाणी हे सगळं आयोजन केलं. यासाठी पुस्तक प्रकाशन करणे हा फार महत्वाचा आमच्या पुढे टार्गेट होतं. ते टार्गेट आम्ही सक्सेसफुली अचीव्ह केलेलं आहे असं मला ठामपणे सांगायचं आहे. आणि याच्यासाठी संपूर्ण श्रेय ऑर्गनायझिंग सेक्रेटरी आमचे सहकारी प्राध्यापक BB पाटील सर यांनी घेतलेलं आहे. रात्रंदिवस त्यांनी मेहनत केलेली आहे याच्यासाठी, हे मला आवर्जून या ठिकाणी सांगायचं आहे. आणि आताच एक वक्ते बोलले, म्हणजे प्राइज विनर होते, कॉन्फरन्स बद्दल रिमार्क दिला की आपण सगळ्या गोष्टी आपण ज्यावेळी इथं येऊन बोलतो त्यावेळी आपण फार आयडियल होतो, आयडियलिस्टिक व्ह्यू न बोलत असतो. परंतु प्रॅक्टिकली कसं आहे, सगळे रिसर्च गाईड्स वगैरे आहेत त्या ठिकाणी. तर प्रॅक्टिकली विद्यार्थी ज्यावेळी रिसर्चला जॉईन होतो आपल्या सिस्टीममध्ये, आपल्या सिस्टीमचं, तर त्याला PhD हवी असते. त्याने एक टार्गेट ठेवलेलं असतं. तो PhD का करतो, तर तो नोकरीसाठी करतो. आणि जे इथं वक्ते बाहेरून चांगला अनुभव घेऊन आलेले आहेत त्यांचं म्हणणं कसं आहे की रिसर्चची काहीतरी क्वालिटी आउटपुट देण्यासाठी आपण रिसर्च केला पाहिजे. तर वस्तुस्थिती एक आहे, आपला म्हणजे ज्या बॅकग्राऊंड वरती आपण काम करतो, आपली इच्छा काय असते तो एक वेगळा भाग आहे. आणि आपण ज्यावेळी ते प्रपोज करतो, मांडतो, आपण यश मिळवतो, त्याच्यानंतर मांडतो, ती एक वेगळी वस्तुस्थिती आहे. आणि ह्या दोन्ही गोष्टींचा आपण मेळ घालायचा आहे आपल्या जीवनामध्ये, तर फार मोठे यश आपल्याला मिळेल. आणि एवढंच मला या ठिकाणी बोलायचंय. आमच्या ज्या ऑर्गनायझिंग कमिटी आहे त्यांनी खूप परिश्रम घेतले. त्यांचं कोऑर्डिनेटर म्हणून मी या ठिकाणी माझ्या 2 शब्दात आभार मानतो. धन्यवाद. असंच आपण या मला सहकार्य करावं, एवढंच आमच्या टीम पुरतं मी बोलतो. आपण सर्व आलात, माझे 2 शब्द ऐकून घेतले. मला होते ट्रॅक जाऊन 2 मिनिटं बोलायला वेळ दिला.
Thank you, sir. Your thoughts are always referential for us. Now I would like to request Mr. D.K. Dhomre sir to propose vote of thanks.
तर व्यासपीठावर उपस्थित असणारे सर्व सन्माननीय मान्यवर, त्याचबरोबर या ठिकाणी व्हॅलिडिटी फंक्शनसाठी उपस्थित असणारे सर्व सहभागी विद्यार्थी, शिक्षक, आता मी काय तुमचा जास्त वेळ घेणार नाही, खूप वेळ झालेला आहे. म्हणजे मी शिंदे सरांना पुढे ढकलत, शिंदे सरांचा काय मूळ शिंदे सर सोडत नव्हते, त्यामुळे शेवटी सेशन घेतला. मोहिते सरांनी तर असं काय वेळेअभावी आपल्याला ते उरकावं लागलं. सरांचं लेक्चर तर खूप चांगलं असतंय आणि प्रेझेंटेशन तर व्हेरी नाईस असते, परंतु आपल्याला वेळ होत चालल्यामुळे ते उरकावं लागलं. तर तुम्ही सर्वांनी सहभाग घेतला. जी कॉन्फरन्स सकाळपासून झाली ती चांगल्या रीतीत झाली. आपली थोडीशी लेट चालू झाली, त्यामुळं थोडस पळवावं लागलं आणि विद्यार्थी संख्या एसटीच्या अनियमित वेळेनुसार त्यांना जावं लागलं, त्यामुळे विद्यार्थ्यांच्या इथे कमी असेल. तर मी एक सांगेन, कार्यक्रमाची कमिटीनं चांगल्या पद्धतीनं ऑर्गनाईज केलेलं होतं. थोडस आपलं दुपारच्या सेशन मध्ये थोडस विस्कळीतपणा आला तरी पण कॉन्फरन्स आपली शेवटपर्यंत कंटिन्यू झाली, हे खूप महत्वाचं होतं. त्याचबरोबर मला दुसरा अनाऊन्स करायचा असेल, पुढच्या महिन्यात 16-17 तारखेला एजम कॉलेज कराड या ठिकाणी इंटरनॅशनल कॉन्फरन्स आयोजित केले. 2 दिवसीय इंटरनॅशनल कॉन्फरन्स असेल. त्याच्यामध्ये 16 तारखेला 3 सेशन असतील, त्याच्यानंतर 17 तारखेला 2 सेशन असतील. त्याचबरोबर पहिल्या दिवशी पोस्टर प्रेझेंटेशन असेल, दुसऱ्या दिवशी ओरल प्रेझेंटेशन असेल. तर आपण सर्वांनी सहभाग घ्यावा. त्याला बक्षीस आहेत आमच्याकडे, पहिला, दुसरा, तिसरा आणि चौथा येतील त्यांना. तर तुम्ही सर्वांनी त्याच्यामध्ये सहभागी व्हावं, पार्टिसिपेशन करावं अशी मी सर्वांना विनंती करतो. आणि हे कॉन्फरन्स अगदी उत्तम रीतीने अरेंज केलं, त्याबद्दल मी सर्व ऑर्गनायझिंग कमिटीला, त्याचबरोबर कॉलेजला, कॉर्डिनेटरला धन्यवाद देतो. आणि माझं चीफ गेस्ट म्हणून 2 शब्द संपवतो ना.
Now I request to Dr. Pisam his addresses.
व्यासपीठावर उपस्थित असणारे माझे एचओडी एसडीएफ कॉलेजचे, ज्यांच्याकडे प्रेझेन्स ऑफ माइंड खूप आहे, ते तुम्हाला जाणवलं जातात. त्या अध्यक्ष चीफ गेस्टच्या व्याख्यानामध्ये सुद्धा त्यांनी त्यांच्या कॉलेजची कॉन्फरन्स आहे हे सांगितलं. माझे क्लासमेट गोबरे सर, ज्या 2 वर्षात आम्ही एकही शब्द बोललो नव्हतो. करेगाव कॉलेजचे कन्या महाविद्यालयाची एचओडी राहुल मॅडम, शिंदे सरांच्या बाबतीत मी असं म्हणेन, अतिशय इनोसेंट आणि अतिशय सिन्सिअरिटी. म्हणजे एखादा नुकताच मुलगा प्रवेश घेतो आणि मला यात मार्क्स मिळवायचे, पास व्हायचे, ही जी सिन्सिअरिटी असते, त्या सिन्सिअरिटीनं अजूनही काम करणारे शिंदे सर. समोर बसलेले कोणत्या ना कोणत्या तरी उद्देशाने बसलेले समोर मोजकेच लोक. काहींचा उद्देश पोस्टर प्रेझेंट केले बक्षीस मिळतोय का, काहींचा उद्देश ह्याच कॉलेजचा आहे, सोडून कसं जायचं. आमचे टोले सर आम्हाला गाडीतून घेऊन आले की सोडून कसे जातील. अशा सगळ्या उद्देशाने आपण सगळे, थोडा जोरचा भाग सोडा, पण अशा उद्देशाने आपण मोजकेच पण दर्दी लोक इथे थांबलेले आहोत. गोबरे सर, मला माहित आहे कॉन्फरन्स ऑर्गनायझेशन करताना आणि शेवटपर्यंत काय काय हाल होतात ते पाहिलेलं आहे आम्ही पण, आणि तुम्ही ते आज अनुभवले. काही का असेना कॉन्फरन्स एकदम व्यवस्थित झाली. जगदाळे सरांच्या व्याख्यानाला थोडीशी घाई झाली, अदरवाईज दीपक डोबल सरांचं व्याख्यान अतिशय शांतपणे आणि अतिशय एक्सलंटरित्या आपण ऐकलं आणि समजलं आपल्याला. शिंदे सरांना वाटते की घाई झाली, पण सर तुम्ही सुद्धा तुमचा टॉपिक, तुम्ही तुमचा मुद्दा सोडतच नाही कधी, आणि इथे तुम्ही तुमचा मुद्दा सोडलेला नाही, तर तेही तुमचं व्याख्यान छान झालं. सकाळपासून ऑर्गनायझेशन चांगलं झालं. मोरे सर जे माझे जुने कलिग आहेत, प्रिन्सिपल असून सुद्धा त्याने आमच्यासाठी व्यवस्थित वेळ दिला, किंवा तो आपलेपणा, आपण म्हणतो खुर्चीचा गुण लागतो, पण असा कुठेही त्यांच्याकडे दिसला नाही. त्यामुळे एकूणच, आणि माझं गाव इथून 7 किलोमीटर, माहेर इथून 14 किलोमीटर, त्या वाटेला येतानाच मला आनंद होतो. माहेरची वाट कधी संपत नाही, आपल्याला माहित आहे तुम्हाला सगळ्यांनाच. तर ह्या सगळ्या आनंदमय वातावरणात माझा चांगला दिवस गेला. कमिटीने अतिशय चांगले परिश्रम घेतले, आम्हाला चांगलं जेवण दिलं, आणि गोबरे सरांना साहजिकच ती आपुलकी आमची एमएससीची असल्यामुळे त्यांनी मला उगीच चीफ गेस्ट वगैरे असं काय 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 म्हणतो लेबल लावलं. काही हरकत नाही सर, आपण परत एकदा एकत्र भेटण्याचा आनंद आहे. आणि तुम्ही सगळे इन्फॉर्मेशन टेक्नॉलॉजी असेल, बायोटेक्नॉलॉजी, मेडिकल टेक्नॉलॉजी, याच्यामध्ये तुम्ही सगळे वाढतायत. कालचं ज्ञान आज शिळ होतं, इतका आपण झपाट्याने पुढे जातोय. मला शेवटी एवढंच सांगायचं की या सगळ्यामध्ये ह्युमन टेक्नॉलॉजी आपण सगळ्यांनी जपूया. बस एवढंच माझी विनंती. धन्यवाद.
Thank you, ma'am. Now I request Mr. D.K. Damle, sir, to propose vote of thanks.
Good evening, one and all. It gives me an immense pleasure to express my sincere vote of thanks for the today's National Conference on Recent Advanced Technology of Nanomaterials. I would like to thank our chief guest for the inauguration function, Professor Dr. K. Varajpure, Sir, Head Department of Physics, Shivaji Vidyapith, Kolhapur. Also, I extend my sincere vote of thanks to the chief guest for the valedictory function, Honorable Professor Dr. J.D. Thoras, Sir, Head Department of Physics, HGM College, Karad. I also extend my sincere vote of thanks for the today's resource person for the session first, Honorable Dr. D.P. Dubal, Sir. Then session second, Honorable Dr. A.D. Jagdale, Sir. And third session, resource person for the third session is Honorable Dr. T.G. Shinde, Sir. Then I also propose my vote of thanks for the today's chairperson for session 1, Honorable Professor Dr. J.B. Thoras, Sir, Honorable Dr. U.K. Moite, Sir, and Honorable Dr. P.Sir, Madam, for help us and cooperations. I also extend my sincere vote of thanks to our Honorable Principal, who always help us, guide us, and encourage us to make this type of seminar and conferences. I also take an opportunity to thank our organizing team, especially B.B. Patil, Sir, Raut Madam, Shinde Madam, Mane Sir, Jadhav Madam, and Gadge Madam. I also thankful for all participants who participate in this national conference. With the permission of President, I would like to announce that today's national conference is over. Thank you very much.
Those who have